all have like double.
We're all united in it. Okay, let's go through the why to make sure we understand it. So you're going to see a question just like this on your quiz next time, but it's not going to be the same question, but it is the same understanding. So let's make sure we understand the why. Now, big thing, right, with any AP question, and I heard great discussions, is it's just figuring out what is the question asking, especially with all the information that's given. I don't know who said it, but over here someone said it in a simplified way, which I really loved. So the question in itself says, in galvanic cells Y and Z, which of the following takes place in half cell 3? So I heard someone say, well, what's happening in half cell 3? Right? Ask questions to the question. So half cell 3 is focused on iron. So all this question is asking, what is happening to iron in Y and Z? Right? That's like a way to like reword the question in a way that maybe makes sense, if just by itself it doesn't. So then, iron in this one goes from a positive number to a 0, because it has no charge. So if the number goes down, we label that as reduction. Think reduction gets more negative, right, since the word reduced. In Z, it's going from 0 to positive, so getting more positive means oxidation. So that's why C is getting reduced and then oxidized. So, any follow-up questions on that for now? Okay, awesome. All right, so let's take a look at, so once again, the goal of today is the mathematical side of these. So each of these could be described as a battery, and this is the voltage they produce. So if you create a battery with aluminum and copper, it has this voltage, and then we're going to learn how to find that number. Okay? So with that being said, those are from last time. I think this is where we're at. Okay, so it's a little weird because it sat over the weekend. Here's our silver and copper reaction we did.
Oh, so it molded up. Oh, it's like gone.
So yeah, I'm pretty sure it's done reacting, like there's no more silver to pull out. So for those that were gone, what happened here is in solution were silver ions, so Ag pluses. We put in copper wire, and then they did an electron transfer. The silver took an electron and became solid. So this is literally solid silver down here. Okay? The copper gave up electrons and went into solution, which is why the solution is blue, because it was clear last week. So one thing went into the solution, the other thing came into the solid. And that's pretty much how all these reactions, the ones that we just saw, were happening. Something was solid and then becoming charged, or charged and then becoming solid. That's the process of oxidation and reduction, is the transfer of electrons. Now, if I separate this into two separate beakers, meaning the silver's in one beaker, the copper's in another beaker, and I hook it up with a wire, that's how then you get a battery, because the electrons will flow. What's important to recognize is the electrons will naturally flow one way, but not the other.
It's the coolest thing ever, silver nitrate.
It is so cool.
Hey, are we gonna do, I just didn't know if I need to find that shrink heating for the periodic trends.
Oh.
Because I'm in charge of the next one. So. You said we may be short here.
Yes, they're in the far cupboard is where they're stored.
In your lab?
You'll see a one that says like shrinking inks, I'm pretty sure, so you can check and see what we're at.
You showing this under dissecting scope so they can see the crystals? I'll bring you a dissecting scope. It's really cool. It's fun.
So I separate this, and that's how you create it. So right now the electrons are transferring in the beaker, but if I want electricity, I have to get the electrons to flow through whatever I'm trying to power, right?
So then you could stick a light bulb on the wire, and it just like as a light bulb, right?
Maybe. I would guess no, because the electrons are going to transfer literally like as the two atoms are touching. So for me to like suck up that electron and get it to go through the light bulb, I would say probably.
From the wire.
Oh, yes. If I have two separate, I thought you meant like in this beaker. Yes. So no, yeah, if I have two separate beakers connected through a wire and I put a light bulb, if it's enough voltage, depending on the volt of the light bulb, it can light it up. Yep. That's how literally a battery works. It's just so keep in mind, electricity is the flow of electrons. If I can get electrons to flow, that's electricity. Okay? Now, what we need to understand is that once again, the electrons will so the natural flow is to go from, wait, which one did we say is getting reduced? The silver. So silver is gaining. So the natural flow is to go from copper to silver. So if there's two beakers, that's the way it would flow. There's no way naturally to make it go the other way. So some things are thermodynamically favored in one direction and not in the other. Okay? It is all about potential energy. Things always flow from high to low, just like things always flow from warm to cold. Now what's really cool, and we'll keep talking about as we go with batteries and things, is it actually is flowing to a state of equilibrium, just like heat. Right? We did this back with our thermodynamics first unit, where I said take your hand and you grab the leg of your chair. Remember this game?
Yeah.
And how'd the chair feel?
Cold, and then it got like.
And then if you keep your hand there, eventually it doesn't feel cold, right? Because it reaches equilibrium. Batteries do the same thing. A battery technically doesn't die, it just reaches equilibrium with the two sides.
So you can add stress to it.
And that's why we need more than two in our little controllers and stuff, because we need a positive, like, we need it to be able to circulate from the positive and the negative.
Yeah, so that's literally like when you plug in a battery and it has like the positive end and the negative end, that's the reference of the flow of electrons. Trevor?
So then how does, I don't know who else does this, but my mom will sometimes take batteries that have died and she'll stick them in the fridge, and then 2 months later she'll pull them out and they work again. How does that work?
What?
Your mom's magical, man.
It just like squeezes out whatever's left in there. It doesn't
Like
fully.
Yeah,
it's not
I'm
like a
assuming
new
that it's
battery?
just like,
Yeah, it's not a new battery, but like it works. Like she'll pull it. I'll be like, go get the batteries from the fridge, and I go pull them out.
but they
and
have been
she's like-
used before?
They have been like. She'll tell me like something will die. She'll say, go put these in the fridge, and so I go put them in the fridge, and like 3 months later we'll be doing something else. She's like, go get the batteries from the fridge. So I go
I'll research more to find out, but I would guess yes, that they're not coming back to life,
Yeah.
but that something about it is just allowing, there were electrons that could have flown, that sounds weird, that could have moved, but they didn't, and something about the cold just allows them to, but I'll look into that.
Tricks you and you put the batteries in the fridge,
Oh,
and then like a week later,
oh, it's
someone buys these batteries and puts them in
Switches
the
it around.
fridge.
I don't know. I don't know what she does. But she does it. I noticed it for like 10 years. Your baggie of batteries.
So, listen to this everybody, ready?
I have batteries.
Give your attention here. So, in your phone or something with batteries, right? As a battery, the electrons will naturally flow. That produces energy. Once it reaches equilibrium, they stop flowing. Now, things that are thermodynamically favored in one direction are not thermodynamically favored in the other. But if I put energy into it, when I plug in my phone, what do I do to the electrons?
Send them back.
I send them back. So you can force the electrons back because you put energy into it, in a sense recharging it, so then they can naturally flow back.
So does it have to be a controlled energy flow back into it to, like, does the energy have to be controlled to recharge it, or could you just put a battery in the microwave? Because I don't think that would work.
No, yeah, so it's not just any type, and particularly it's more like electrical energy, not so much heat energy.
So if you
So what we need to connect first here is that a positive voltage represents a thermodynamically favored process. So as this is written, this naturally happens because it naturally produces positive volts. If something has negative volts, then that means it requires that energy to happen. So the way I kind of remember it is because batteries have a positive voltage, like a 9-volt battery, right? That is a spontaneous process. If you were to buy a battery with a negative voltage, that means it's like gonna suck energy away. It'd be a very poor battery, right?
What are the words that are like
Right on the line. So cell potential is what we call this E number. So when we talk about this value, this is called the cell potential, and it's also EMF. The oomph is how I say it. The oomph of the battery. But it just describes that process of the electrons flowing. Okay? All right. Our equation, here's kind of a visual to show. So once again, here's like your battery, the positive and negative end. It will always naturally flow from high to low. If I want the waterfall to go backwards, I have to put energy into it to make it go the other way.
I mean, you can't make a waterfall flip backwards.
You're going to flip up a waterfall.
I mean, you could, like, you know how, like, water goes, like,
I think I've been to
Yeah,
that.
but then it would require energy, right? So,
could you use the waterfall to put well, not like, it wouldn't be as much water, but it would like, put it back.
yeah, to be perfectly, it wouldn't be perfectly conserved, right? So. All right, this equation for cell potential, or the oomph, is not on your formula sheet, so make an extra star off to the side and say not on my formula sheet. But hopefully you'll recognize that it's a very simple equation. I know, it still drives me crazy that they just choose to not put a few on. So to calculate the overall cell, so that means so keep in mind, this is overall.
So oomph is different than E.
Say that again.
Never
Yeah,
mind.
that is
My brain just blew up.
Oh,
I'm sorry.
Is E cell
That makes
Yes.
sense.
So the overall power of the battery is equal to the voltage of the reduction plus the voltage of the oxidation. These are individual values. So pretty much you just take the individual values and you add them up.
Oh, I don't think I'll remember that. That's not that hard.
Not too hard to remember. Now, with that being said, keep in mind it's somewhat similar to Hess's law in heat. That heat was an additive property, right? Where if this reaction released this much heat, this reaction releases this much heat, and then we look at them together, we just added delta H's up. The one difference between heat and voltage is voltage is not extrinsic. Meaning, if I add more, let me go back to our last one right here. So like this equation, wrong way. So like this right here has a 1.10 volts. If I were to say, oh, well, let's times everything by 9, like in heat, the heat times is by 9. If I have more wood, I get a bigger fire. Voltage isn't that way. The voltage is still 1.10.
Just lasts 9 times as long.
The battery will last longer, but it doesn't actually increase voltage.
So if you want to increase voltage.
That's why there's like big D cell batteries that are like, they're still
That's
1.5.
Hold that.
Add more
Still
cells.
1.5 volts. But
More cells, yep, so you can have lots of cells of them.
Say
Like, that's what
you could power jump these balance forward with a really big battery, but it wouldn't last as long as if you put a lot smaller.
Possibly, yes.
So then is a 9-volt battery like a different reaction entirely?
Yes.
And then a car battery is even different. Because like, aren't car batteries like 35 volts?
I'm not sure off the top of my head. But yes, so definitely, so there's a combination of one, more cells, because cells are additive if you have lots of zinc cells. And
Not relatable.
Or there is a way to increase it within a single cell.
Loving myself, not you.
Okay, let's look at a problem here. Oh, let's look at our chart first. Okay, so this right here is a chart that shows the values for reductions for a lot of different processes. Now, you do not have to memorize this table, okay? They'll definitely give you, we're gonna reference it a lot today, but most likely on the AP test, they're just gonna give you a small table for that particular question, right? They don't really do like, look at this big table and find what you need, which is kind of easier actually. So let's label though what this means. So notice that all of these are written as reductions. They're all gaining electrons, and then this is the voltage that results as it gains those electrons. So the ones at the top of the table, notice fluorine has a very positive voltage. What does it mean to have positive voltage?
Thermodynamically favored.
Thermodynamically favored, spontaneous, it wants to happen in that way. So label that box as most likely reduced. The more positive the E value is, the more likely it's going to be reduced. Now let's go kitty corner. So come down here.
Four square. No. Four corners.
Four
Remember that
corners.
game?
There you go. Yeah.
I love that game.
More likely.
Can we play that game after the test?
Most likely
Let's
oxidized.
put it on the list. So then these ones are very negative. Do negative things naturally happen?
Love that. Order heads up.
No. So if I flip this and make it oxidation, that becomes positive, which,
More likely.
so these ones are more likely to be oxidized. So when you're looking at where the electrons are going to flow, it's a big matter of what's going to provide me the combination to get a positive E value. One of them's always going to flip inside because something has to be reduced and something has to be oxidized. These are all reductions. These two things wouldn't react as is. The one that flips is the one that is more negative because you want it to be positive overall.
Does it just flip the sign?
Yep.
Same number? Okay.
Yeah, same number, just so that since the equation flips, the sign will flip. Yeah.
So if you were trying to figure out the voltage of like a battery made out of two of these, you would get that value plus the other value.
Perfect. Yep. So if we were to make a battery of lithium and fluoride, right, we would just add 2.87 plus 3.04 because it flips signs.
Okay.
And that's why lithium ion batteries are,
Are the best ones.
Is there lithium fluoride on it?
I don't know if they're fluoride, but lithium by its, lithium with anything gives you a lot of voltage, right? So, any other questions so far? Okay,
So
let's
how
try
do
a
you make
problem. Oh, put a big star next to this because I already filled in your blanks. But this is just what I just said.
Oh.
Okay? That the greater the driving force for reduction, right, keeps it positive. So the more positive E value is the one where reduction happens. Yeah?
Okay, so why do we need to flip the sign when it's more likely oxidized? Just like,
So you're always going to pick 2 from the chart.
yes.
But the chart's written as only reductions.
Oh, okay.
Oh, just the opposite. So
Oh,
Least likely reduced.
yeah.
least likely oxidized.
So we're looking at, because we have to do the oxidation and the reduction,
Yes.
so we're looking at that plus those bottom ones, which will be flipped because it'll be the oxidation.
Yes, you always have to have one at each, but
Okay.
one has to be oxidized.
Okay.
Does that clarify it?
Yeah.
Do electrons always flow towards the reduction?
Yes. Yeah. Unless you're supplying energy to make it happen. But spontaneously, yeah, they're always gonna flow to get a positive voltage. So, okay, kind of going off of what Harry just asked, let's look at this question. So this question says we have 2 processes. We wanna know if we were to create a battery out of these 2 things, which way is it gonna flow, meaning what's being oxidized and what's being reduced, and then what is the cell potential? What is the voltage going to be? So step 1 is we need to know what voltage these have individually. So look at your chart. Let's find cadmium. So the value for cadmium, I should have just put them on there.
-0.4.
Okay, so -0.40 is cadmium's value. And then, now be careful because there are multiple tins on the list. We need the tin 2+ version. So tin 2+,
Negative
what was that?
0.14.
Thank you. Okay, so those are the values written as is for how these are written. Okay? I just took those from the chart.
When they're reduced, right?
They're both reduced. So we need to figure out which one is going to flip and actually be oxidized and not reduced. I think the overall goal needs to be positive.
Yes.
So which value needs to flip for it to be positive overall? The more negative value.
Wait, so why exactly do we need it to be positive?
Because positive means spontaneous. And if I want to create a battery, I need it to be spontaneous.
Gotcha.
Okay, so this one is going to flip because it's getting oxidized.
Isn't SN2 plus 0.15?
Did we look at the wrong one?
Oh, 4 plus.
There you go. I know, the numbers are tiny.
It's a struggle.
Okay, everybody good while we flip
It's a
this?
struggle.
Okay, so what is the, like, the statement at the top of it that we start, like,
What are you asking?
the statement that we started, that's about this, the one that we just did before. So what does that mean? Like, so, which one's the cathode and which one's the anode?
Right there.
So let's do oxidation and reduction because that's really more, and then we can label cathode and anode with it. So this one is flipping, which means this one is being oxidized, so label this. So this is oxidation. This one is going to be reduction. If I were to write the overall reaction, I would just flip this and then I could add them together. Right, because the oxidation is the other direction. And then for the overall voltage, now that I flipped one of them,
We just add them.
you just add them together, so the overall voltage would be
26.
26.
I am literally a genius. I won. I never do math.
Good job, Karen. Proud of you.
Questions so far? Now, anode and cathode are words we use. I honestly probably should have just gotten rid of it because on the AP test they focus more on labeling reduction and oxidation. But once you have this labeled, electrons always flow from anode to cathode, meaning they always flow from reduction to oxidation.
It's like,
Oh, I said that backwards.
No, yeah.
Because you lose electrons, you gain electrons. So the anode is always the oxidation.
so if it goes anode to cathode,
What
you
is
can
this?
remember it by saying A goes C goes B.
Wait, it says in the, thing, it says like the one that has the more positive value is the one that's the cathode.
I'm gonna actually
Oh,
Before you flip signs. So if I don't flip this sign, this is more positive than that.
so it always flows from cathode to anode.
And it's small.
Oh,
Because oxidation means.
the electrons flow.
Yes. Did that answer your question, Joel?
But they don't have it on
It
It was
goes,
just weird to read.
Yeah. I don't, honestly, and that's where I'm like, I don't know. If I keep studying AP tests and they just never use anode and cathode, I might just not talk about it. They just sometimes confuse it. Any questions so far with given values, identifying what's being oxidized, what's being reduced, and then the overall voltage? Okay, let's try a practice problem. I'll do one more with you, and then I'll have you try one for smiley face. Same concept, just different look to the question. So this one gives us a reaction that's already written as oxidation and reduction.
Okay.
We want to figure out, is it spontaneous as written? What does that mean for my E value if it's spontaneous?
Has to be positive.
Positive, yeah.
when it says standard conditions, it's just the stuff that we're used to.
Yeah, it's just that table, if you're not under standard conditions, this table isn't valid anymore.
Will it ever give us different conditions?
Not in this type of question.
Okay.
We'll talk about non-standard conditions at the end and like how you might have to deal with it, but not for voltage calculations. It gets too complicated. Okay, so step one, we gotta figure out with how this is written, what's being oxidized and what's being reduced. So I match my copper. Copper is going from 0 to +2. So that means it's being oxidized. Hydrogen is going from +1 to 0. So it's being reduced. So now I go to my chart, find hydrogen's value, which is 0. So we have 0 plus. Now I need to find copper's value and do what with it? With it, because it's being oxidized.
Oh, flip it, right?
So copper 2 plus.
Is it 0.34?
Yeah, so I'm gonna write it like this just to emphasize the sign flip. So we flip the sign because it's being oxidized.
So this one.
So it's gonna be a negative.
So the overall is negative 0.34, which is not spontaneous. I would not keep put those things together, it naturally would do nothing.
Can we abbreviate spontaneous as spon?
On the AP test, no. On all homework assignments, yes.
Okay.
So, but hypothetically, could it go in reversal then?
Totally. If I put these together, that's probably what would happen, is it would start going in the other way.
You're like, go.
That's not what I wanted, but yeah. Because if it's not one way, then it's going to be in the other, right? Yeah. No, great observation. Okay, I'm going to give you 2 minutes for a smiley face to determine what is the E value and then is it spontaneous or not. Okay? Ready, set, go. Yeah, put your final answers on your board. So what I want to see on your board is the E value and spontaneous or not.
The I is
So it's gonna be, I hate math. So,
plus the reduced I is the yellow I.
Oh, it's like,
Okay,
do we have to find the actual value, or
Is yellow?
can we just?
Is yellow negative? Yeah.
I want you to find it just so I can know that you know how to find it. Technically in this question, no, it doesn't ask for it.
Okay, so now we have those. Let's try. So first is nope. Does it matter which one we do first?
Not really. You're just adding them. The biggest thing is knowing which one's left inside.
I don't
I understand the tiny, and the other stuff, it's gonna be like,
The biggest thing really is like we understand like the nitty gritty of the battery. That was the molecular view. That was zero, right? And then the big thing on Wednesday was like these are easy to see, like 0 to 2. Sometimes it's not easy to see. So learning how to find the numbers when it's not.
Yesterday's in 2, and I just do that.
no way you didn't. You didn't. You didn't. Found?
Yeah, because my first word was today's
It might just mean that it's just like the
There was anything that you didn't think about? Why didn't you? Today's riddle was, I got a divorce, so it wasn't bad. It was the same.
whatever reason, it's just because you could have two tables.
What was it again?
Oh. Let's just do one table and then you just
I never got any yellow. I'm literally cracked. Let me see it. Let me see it. Let me see your progress.
So how can these combine to make it positive? But then what you know is that this is not just matching Just to remind you, there's only a trash. It's just a so this one side has these signs, combine them together. Alright, so on your board, what I want to see is your E value and whether it's spontaneous or not. I'll give you 10 seconds to write your answer on your board if it's not there. 10, 9, 8. So I want voltage and spontaneous or not. 5, 4, 3, 2, 1. I don't know if I should give that to you.
You're not that far into season 3.
No. I was hoping to explain that to her. All three of us are working together.
All I know is when I turned around, you were just looking at a book and Zoe was writing.
We did.
So
We solved it.
I'll let
and
Zoe
then she
decide
wrote-
if you.
I'm sure I promise you we wrote this down.
Wait, show me your answer. Show me your answer. So there's 2 smiling faces here you can earn. Good job, guys. I think we all got it though. So you should have gotten a 0.82 voltage, which means yes, spontaneous.
So wait, how many smiling faces? Just one?
So 1 for the voltage and 1 for saying it's spontaneous. Okay.
I'm getting so many
Oh, buddy.
Alright, now what we're going to look at, everybody, is the connection. So we've talked about 3 thermodynamics functions, or 3 things that can describe whether something is thermodynamically favored or not. We've talked about K, equilibrium constant, delta G, and now E. Now we also talked about H and S, but those by themselves can't determine thermodynamics favorability, right? Because those together make delta G. But delta G, E, or K by themselves, you can claim by knowing that value, like, yep, that's thermodynamically favored or not. Let's write down off to the side really quick just the connection. So what did we just say? What does E need to be thermodynamically favored? Okay, so for something to be thermodynamically favored, this is a mouthful. Okay, so thermodynamically favored means a positive E. So positive volts means thermodynamically favored. What does it mean about delta G?
Positive.
Delta G
Negative.
We're multiplying it by negative.
So we want negative delta G for it to be thermodynamically favored, because keep in mind the negative is like it's coming out of the system. It doesn't cost to use it. And then the other one was K, so equilibrium constants are negative or positive.
It's less than or greater than 1. Not less than or greater than 1. Yes.
Okay, so one's the middle ground, so what do I want to be thermodynamically favored?
You want it to be less than.
Do I want more products or more reactants?
More product.
More
Good.
products.
Meaning?
Yeah, so it has to be greater than 1.
Greater than, so K should be greater than 1. So all 3 of these should be linked.
Where's K?
We'll bring it, it's not in this equation yet.
Oh, okay.
It's coming.
It's coming in that red line.
So, but recognize, like, if this is true, these have to be true.
Then what's X? Can like make it back?
We'll get there, you're getting excited for your math, Sophia. So, does that make sense, though, this connection? Because pretty much, like, you should know, if you get this, and then a positive delta G, that should be a red flag if you did something wrong, because that's impossible. Something can't be thermodynamically favored in one unit, but not the other. They have to match. Okay, now this equation is what connects E and G. So if I have one, I can find the other. So G is good free energy. E is our voltage. F is a constant, known as Faraday's constant.
Who?
Faraday.
I only know how.
It's on your formula sheet.
Is that number of volts?
It's 96,485.
What's the unit?
The units are coulombs per mole of electrons. And yep, it's linked to our concept of a Coulombic attraction.
So, man.
What's the top word in
Coulombs is what it's
I love good Columbus.
Coulombs.
Coulombs over
Moles of electrons.
moles.
Christopher.
Is it still?
And then I'm guessing that is the number
DBIL.
So just like in perfect N is moles, but specifically for this, it's moles of electrons.
Do you have to memorize Coulomb's constant?
No, it's on your formula sheet.
Cool.
It's actually Faraday's constant.
Get it?
Say what?
It's actually Faraday's constant.
Okay. Everyone have that down before we try a problem with it now? Electrons. So like how many electrons are being transferred in the oxidation reduction process? Okay, let's try this problem now. So we're gonna connect. We're gonna do 3 equations in this one problem. This can actually be a good review of past equations we've done for this unit too. One thing though, if you are not in the habit of, as we start our review month, okay, you start doing lots of practice tests with questions from the whole year, okay? If you're on the FRQ section and a question says calculate, and you aren't looking on here, and you don't know what to do, look here. Okay, like 99% of the problems that say calculate have an equation right here that you just need to find, figure out what they give you, plug that in, there's your answer. Okay, so if you're not in the habit of, when a problem says calculate, looking here, start looking here. It will help you a lot.
Takes you back to like literally every problem.
Is on the formula sheet.
Dude, I lived by that equation sheet.
Is David Brown to check out?
Yep. Question.
So for this equation, how is oxygen the only one being reduced?
Oh, thank you. There's a typo. So first off, scribble off this plus sign. That's not supposed to be there. Scribble that off. Okay, so we're gonna find E, G, and K numerically.
So 298 is standard temperature.
Yes.
What would happen if it wasn't good?
So if you're not under standard temperature, these values aren't true anymore. So
Is that the only thing about
no, it affects like a lot of other things too. Like you're not like the pH scale only works at standard temperature.
What is standard temperature?
298 or 25 degrees Celsius. So
How much is that in dollars?
I don't know what's 25 in Fahrenheit.
Give me a second. I have
But yeah, so and there are ways to calculate it outside, and we'll kind of look at it mathematically. Though you'll never have to because it gets quite complicated. But I will actually show you the equation of how it does convert if you're not
I
understanding
literally, this is on the AP test, or ACT test, I'm not even
Question
kidding.
here. On like the multiple choice, will they ever say like, this equation has a negative G? Estimate if it will have a positive P.
Totally. Yep.
Wait, how many degrees Celsius?
25.
So you say false.
It's 77 degrees Fahrenheit.
There you go. Whoever asked for normal speed. Okay, I'm writing 3 equations up here because we're going to use all
77
3.
degrees Fahrenheit.
Oh, it's way too hot. My house is like 71.
Okay. So once again, take what you know, and then we're going to connect it.
Oh, that's the cursive L, right?
Yes, natural log of K. All right, so step 1 says using the standard reduction potentials, we want to eventually calculate delta G and K. So I want to get this and I want to get this, but using reduction potentials means, yes, it's from a while back. It's natural log is what that is, ln.
Is that the same as that? Can you find the same?
They're all on, these are both on your formula sheet, by the way. This one's not. No, so this is our practice with it today. Okay. All right, so coming here first. So we need to figure out what's being oxidized and what's being reduced to then pull their values from the table.
Okay.
So silver is 0, going to +1.
So it's reduced.
So silver is getting
No, it's
oxidized. Okay. Oxygen is at 0, and it's going to, now this is where if you were gone the time before, if it's not as clear, we have to use oxidation number rules. So what's the rule for oxygen?
It's
Negative 2. So oxygen goes from 0 to -2, which means it's being reduced. And then hydrogen didn't change, which is why I'm ignoring it, because it's +1 and +1. Okay, so go to our table and find this equation of O2 becoming 2H2O. And what is its cell value?
Ooh,
Point
0.7.
No,
What?
it's in the wrong way.
Yeah, so look for O2 becoming H2O.
Yeah.
1.23 positive. Did everyone find that value?
Wait a minute. 1.23.
Yep, I support that. Now, notice there's other things in it, but what you're just looking for is same thing on the left, same thing in the right.
Oh. I
So do
see.
you guys see how it's O2 on the left, 2H2 on the right?
Yeah, there you go.
Everyone found it?
There we go. Yeah.
Okay.
I wasn't looking at the arrows.
Is it ever possible to have more than two, like,
No, if I'm understanding your question, so you'll only ever have one thing get oxidized and only one thing gets reduced.
Okay.
Yeah, great question. So then let's find silver. Find silver on your chart. So it's 0.8, is that what I'm seeing?
Yeah.
And then we gotta flip its sign, because it's being oxidized.
Am I not seeing it? Oh.
So voltage would be,
My number.
I don't know.
Oh, it's
Oh yeah,
times
0.4.
Wouldn't it be 4 then?
no, we don't multiply.
So
Because
0.4.
no matter how many, it's the
It,
same.
it doesn't change the voltage when you have more.
No, it's not. It's 0.7. It's 4.7. No, it's 3.7. No, 3.
It's
Point-
4.43.
So I was right.
I'm hearing lots of numbers, but they do not sound right.
It's literally just 12 minus 8, so it's 4, and then you just
Okay,
Yeah.
add 3 on the
Good.
end.
now that we have this, I'm gonna plug it in over here. Alright, switch your markers. So N is what again?
N is the moles.
Moles
So
of electrons. So this is where we have to go to our equation and look at how many electrons are transferring. Now this is where
Oh,
the
is it moles
4
of electrons?
does come into play.
Yeah.
So I'm going from 0 to +1, but there's 4 to 4, so that means there's 4 electrons being transferred.
Oh.
Okay, so is it just 4?
So N is 4, yes. So 4 moles of
Wait, you don't have to
electrons.
say to count the other numbers?
No, because whatever
It will
gets
always be the
reduced
same, right?
should be what's oxidized, so I just pick whichever one is easier to track. Because the oxygen one's like a little messier to figure out.
Okay.
But yeah, it has to match, so. Good question though. Okay, F is our constant. 96,480, I already forgot my number. 85? Thank you. And that's coulombs per moles of electrons. And then E is our voltage right there. 0.43 volts. Plug that in and it's really big. I don't remember.
That's a big number.
Yes.
165,954.
How do you know that? How do you know the coulomb? 659.
Is that just the unit?
54.
It's a
So
constant.
it's the same number every time.
2?
That is great, but this is
Coulombs over
Okay, units get a little weird, but if this is also actually on your formula sheet, this relationship. You can also remember that delta G always just ends up in joules.
Really?
But the way it works out mathematically if you're tracking units
It's coulombs
is that
times volt.
1 volt equals 1 coulomb over 1, oh I think I did that backwards. 1 joule over 1 coulomb. This is on your formula sheet, by the way.
What the heck?
So a volt equals this.
But we can't.
So
look
if
at
I want to
coulombs.
get
So we're-
coulombs by itself,
We're looking
a
at
coulomb is a joule over a volt. And so then the volts cancel, the electrons cancel, and you're just left with joules.
Oh.
And it will always just be joules, so if that makes it easier.
Oh.
I'll send even.
Isn't that big number negative?
Yeah.
Thank you. Yeah, don't let me lose that negative sign, because otherwise that doesn't make sense, right?
Okay, that is what I was.
Is that what you're gonna say too? So
Yes.
this is positive, that must be negative.
I had no questions about that. I was ready to follow through to the very end.
Me too.
Okay, good so far? with all of our algebra? It's mostly ordinary.
Why are we doing this work?
Because it also wants us to find
So we're looking at a spontaneous reaction.
Okay, I'm gonna slide this over.
Okay, so we're looking at delta G.
Okay, come into this one, everybody. Now, I'm going to rearrange it to get K by itself first, and then plug in my numbers. That's how I like to work with equations, is just move the letters before I plug in numbers. So follow along with me, because it is...
I'm at the glare, hold on.
Oh, is it sunlight right on this? Okay, so if I want to get K by itself, what would you do first?
We would divide the RT and ln.
Good, so I'm going to divide by, so we're going to get delta G over, that was a weird G, negative RT equals the natural log of K.
Oh, so the K and the
And then it
natural
would be.
log. Oh, because we need to do the
Yes,
natural
so
log.
in
whatever.
math, the way you get rid of a natural log is e to the power of that thing.
I've never done that before,
Yeah.
so rock
Well,
on.
now we're teaching it. So to get rid of a natural log, you do, so then it would be K is going to equal e to the delta G over negative R. It's a constant. Think of it kind of like
It's
the button on your calculator.
It's the opposite of natural.
It's the opposite of the natural, it's the inverse of the natural log,
Yeah.
but it is a constant value. R's the gas constant, T is temperature.
Which is what again?
Oh, we'll keep it in Kelvin, so this is.
That got weird.
Okay, first off, questions on getting here to here. Because this is on your formula sheet, but this is not.
Yeah, because we're trying to, okay.
So you need to know how to be able to rearrange it. Okay, so then when I plug this in, I would have e to the,
Which R do we use?
this number, 16595 gives you 2 joules. And it's negative, bring the negative with it. Over negative R, so negative R is 1.31.
I just got really scared.
My brain hurts.
Wait, ours?
16595.
What's R?
Oh, wait, what does that fit?
It's just a constant. It's actually the same constant used in Pervnert, just different units.
Oh, it's a big number, like a big
Yes, when you
number.
want ATM, but because we want joules. So here's your R's, there's lots of values for R, but we want the joule units, so we'll use this first. But it is like the same. And then times that by 298. So when I type this in my calculator, I would type all that in first, and then do e to the answer. That's how I would choose to type it in.
Oh man.
It's like, I can't remember the first part, but it's times 10 to the 29 is the second half.
Wait, how do you?
Yeah, it's
It's 1,000 volts.
It's
basically. 1,000 volts of.
You can do the bottom first, and then divide the top by the bottom, and then just make e to the power of your
I hope that's it.
Okay, so.
Where is e?
Single reactor.
I'll figure it out.
There is.
Wait. Did
Hey, I got it.
So I'm typing that in.
1,000 moles of product for one half reactor.
So definitely very thermodynamically favored, right?
Okay.
Yes.
Exactly.
All the numbers, right?
All right, questions on all that math?
Yeah.
So, why is the E?
That's
So the best way to explain if you haven't learned in math is E is the inverse of the natural log. So just like how if I want to get rid of something that's timesing, I do the inverse by dividing. So if I want to get rid of the natural log, I have to do the inverse of natural log, which is e to the power of that.
Grant, you want a math lesson right now? I can give you a math lesson right now. No?
That's my simple answer for now. Pretty much just know there's a button on your calculator that is e to the power of.
It's above that line.
Did I set this up right or did I miss it?
I
I need to put a parenthesis for the
all the bottom.
negative point. Yeah.
Yeah, put a parenthesis. So, any other math questions for now?
We did that to find K. because guys are always asking.
It also takes the amber delta G too, but
you need
we couldn't get it without. Yeah.
So will there be a question like this on the side? That needs all three things?
In one?
Yeah.
I don't remember. I mean, I would know how to do it. I don't think there's one for this test, but on the end of your test, definitely.
Wait, where's the E? Is the E like the?
Use algebra to find.
That's pretty much all it is. It's just algebra.
It's above the divide.
It's above the divide?
I think so. What? Wait, do you have a chemistry?
No, yeah, isn't it this one? E to the power of X? Yeah.
That oh wait. So you can just do your E button again. See how it says second answer.
No way.
And that will just, you don't have to retype it. I gotta teach you guys all the calculators. So, okay, everybody stand up. 30-second stretch break, and then we just got 2 more things to talk about. And then no more math. So it's not too much.
I just did it. I got it, yeah.
Okay, take a quick stretch break. It's 2 more things, but it's only 2 more slides, so it's not like they're not big.
Yeah, but it's 2 things in like 10 minutes.
I know, that's 5 minutes per slide.
Can you imagine?
I figured we could find a Google person that just teaches me everything I need to know about the times. And then I just did the notes and I'll just do the whole. I can I'll figure it out.
I mean, I have videos that literally go through it.
I don't know what happened there.
You went to California.
Okay, here we go, guys. So, we're actually now going to address Milo's question at the very beginning, and then how do we increase voltage of a single reaction? So, all the reactions we've been looking up, and you guys have brought up a few times, are under standard conditions. So, there's a few things that play into standard conditions with batteries. One is the temperature, another is the molarity of the solutions they're in. Standard conditions is the molarity of 1. If you change the molarities, you can actually change the driving force by making it a non-standard cell. So what we have here in this picture, I'll give you a second to fill in your blanks, and then that way you can listen to the description. Keep in mind the big thing is that electrons flow to get to equilibrium. So if you can disrupt that equilibrium balance even more, you create a greater driving force to get there, hence more voltage. So we're going to look at, it's a big relationship of Q to K. Because once it's at K, then it's going to stop. But if there's a big difference between them, then it's going to increase that voltage. Okay? So notice with this battery setup, the beaker on the left has a lower molarity than the beaker on the right. Electrons are flowing from the anode to the cathode like ours, so spontaneously. Don't say anything out loud, but from what we talked about last, this is like the before, this is the after picture once it's reached equilibrium. Notice once it reaches equilibrium that the concentrations are now the same. Equilibrium out here, right? So why will this concentration go down and this concentration go up as the battery works? Don't say it out loud, but think in your head. Why is this one going to go down and this one go up? And you can kind of see it from the colors too. Notice like it's clear and green, and then both of them are like slightly green. Okay, Sam, let's hear your idea.
Okay, so on the side where the electrons are going to, it's making it more negative, and so more positive things are, wait.
Keep going.
Yes, the more positive things are going onto the electrode, but I forgot which one.
You're good.
Cathode. And then, yeah, on the other side, the opposite. They're coming off of it because it's becoming more positive.
Very good. So this one is dissolving, raising this concentration. This one is pulling out, reducing its concentration until it becomes C.
Oh, I need to
Does
write
that make
that
sense?
down.
Have a smiley face, Dan. Well
So
said.
minus and I plus.
So if you create a very big difference, then that's where you can increase the voltage. What's cool is actually, this is an example of you can actually create a battery with the same substance on both sides. This is a pure nickel battery. It's nickel and nickel. But you're simply driving the force by creating that difference of concentrations.
So basically, it's just an equilibrium.
I'll lift you in my arms.
Pretty much.
So you're just saying that it's just trying to get to equal concentration? Okay.
Yep. Yep, in the end, or yeah, it's gonna keep flowing until it gets to equal concentrations and then it stops. Because they always flow from high potential to low potential, and so that difference of the difference of the concentrations provides that flow state.
Trying to recharge.
So yes, good observation. Any other questions on that? Now, from the beginning, Sophia brought up the question of then, like, how do rechargeable batteries work, right?
Oh.
And we mentioned that you have to plug them in to make them go back. Vocabulary word for that is called, oh, I missed this. I'll come back, let me finish my sentence. That is called an electrolytic cell. So electrolytic cells are not spontaneous.
I'm sure.
They require energy to go back. So that's just the name for the opposite.
None of, like, it's never spontaneous?
Yep, so as written, it will never happen on its own accord.
Oh, that's kind of cool.
Okay? We'll come back to that. I was just finished, my train of thought was connected, so I didn't want to break it. Now, there is a box right there of another equation that deals with battery calculations. It's on your formula sheet, so it's just another one where if you see something about current of a battery, so I is for current.
Because there's too many Q's.
And then it's charge over time.
Is that Q?
Yeah, it's a Q.
Oh, my.
So just another calculation you can do when dealing with the batteries. You can figure out its charge or its current in relation to the time. Once again, just pretty much recognize if they say the word current and then calculate, you're going to use this equation. So going back, and this kind of deals, it is on your formula sheet, yeah. Okay, coming back to this one. This is pretty much what we just talked about. So let's put it in here. So the whole idea is for Q to become K, right? So let's review here. So what is Q equal again? Good. Which equals?
Products over
Yeah,
reactants.
please listen. So Q is products over reactants when I'm not, oh, come on, can't write,
Not at equilibrium.
not at equilibrium, or I don't know I'm there yet, right?
Yeah, unknown equilibrium. Unknown.
So keep that in mind. So Q is product over reactant. So that's why in the beginning we said if I times everything by 9, it doesn't increase voltage because in a sense, they both
They
get
just-
times by 9.
So it's just gonna be 1.
So it doesn't change.
It
So
doesn't
if you times one side of it by 9.
So that's where you can increase voltages by increasing one or decreasing one and not the other. But the catch is, if I want to increase K,
You have to decrease.
what do I want my Q to be? Do I want Q, if I want to drive to product, do I want Q to be greater than or less than 1?
You're gonna want to be less than 1 because then
If you
you're
want more
trying to.
product, no, greater, it would be greater.
So we want, so not K, but Q.
In order to get to K, we need to have a lower.
If you want more products, you have to
Good.
have
So
more.
I want Q to be less than 1 so
Yeah.
that it drives to the product.
Would you put more reactants?
Which, that makes sense, right? That if you put more reactants in,
It'll
it
react.
should help you get more product.
Oh, what you're saying is you want more products, you don't have more.
Yeah, so I want this situation so that it can naturally create more product. And yet, it's just like the chat the again. So,
I feel like I'm like half understanding.
questions on that?
You know what? I'm just gonna work on it, see how it goes. Cause like I have like a small kind of amount of understanding, but I feel like
I understand what we
they're not. It's not clicking.
There you go.
Okay, just a reminder of some helpfuls. Okay, this is like a checklist if that's helpful to you of like everything that went over. So when you're making your review sheet or thinking about like, do I know everything I need to know? You can use this checklist. The review on Canvas, once again, will have AP style type questions. So use those as a way to check yourself. And if you don't understand them, I'm going to try to add like helpful hints. So if you get it wrong, it can like help you understand what you did wrong, stuff like that. So I know, guys, it is a whirlwind, but make it to Friday, and then you can breathe through spring break. Oh, you take the AC on Saturday? But then you'll get enjoy your spring break after.
Well, but it's still general conference.
One step at a time, right? So, no general questions?
Let's be honest, dude.